A container ship in a severe storm does not look like it should survive. Thousands of steel containers rise high above the deck. The bow disappears behind walls of water. Then the entire vessel begins rolling toward the sea. The horizon swings from sky to water and back. For a moment, it looks impossible that something this large, and apparently this top-heavy, could ever come back, but it does, and the reason has surprisingly little to do with what you can see above the water. Chapter 1. The force that pulls it back. The question is not whether the ship rolls. It will roll. The question is why the roll stops. Every floating object lives between two forces. Gravity pulls downward, concentrated at a single point, the center of gravity. Buoyancy pushes upward, concentrated at the center of the underwater hull. When the ship is upright, these 2 points align. The vessel floats, but the moment a wave shoves the ship sideways, everything changes. The center of gravity stays where it is. It is locked to the mass of the ship. The center of buoyancy shifts, because now more hull is submerged on the low side and less on the high side. Buoyancy moves sideways, toward the deeper water, and that creates leverage. Gravity continues pulling downward through the ship's center of gravity, while buoyancy acts upward through its shifted center of buoyancy. The separation between those lines of force creates a restoring moment that tries to rotate the vessel upright. Naval architects describe that restoring leverage using something called the righting lever, or GZ. And at small angles of heel, one of the key measures of initial stability is metacentric height, GM, the distance between the ship's center of gravity and an imaginary point called the metacenter. But that still leaves an obvious problem. If thousands of containers are stacked high above the deck, should not the ship's center of gravity be dangerously high? Chapter 2. The weight you never see. Look at a container ship from the dock, and your eyes go straight to the stacks. 10, 12, sometimes 15 containers high. It is natural to assume that is where most of the weight lives. What you cannot see is everything below the waterline. The main engine alone can weigh over 2,000 tons. The hull is not a thin shell. It is a massive steel structure of frames, stiffeners, bulkheads, and double-bottom spaces. Below decks sit generators, pumps, fuel, fresh water and machinery weighing thousands of tons, and beneath all of that sits ballast. Tanks built into the double bottom and sides of the hull can hold tens of thousands of tons of seawater, helping the vessel maintain safe stability, trim, draft, and structural loading. The ship looks top-heavy because most of the weight below deck is invisible. Chapter 3. Balanced before it sails. A container ship does not load itself by chance. Before loading begins, planners already know the verified masses and destinations of the containers scheduled for the ship. Before a packed container can normally be loaded, its gross mass has to be verified. Under international rules, that can be done either by weighing the packed container itself or by calculating its contents and adding the container's tear mass using an approved method. That verified weight reaches the terminal and the ship in time to become part of the stowage and stability calculations. Specialized planning software assigns positions while the vessel's loading computer checks what that arrangement will do to stability, trim, and hull stresses. Weight matters enormously. Heavier cargo is generally kept lower where practical, but planners are solving several problems at once: stability, structural limits, destination sequence, and the permissible loads on each stack. The result is a three-dimensional map of weight across the ship before it sails. But even after every container has been positioned, the ship carries another cargo that almost nobody sees. Chapter 4. The invisible cargo. Water. Enormous ballast tanks are built into the bottom and sides of the hull. Seawater can be taken aboard or discharged to keep the vessel within safe limits for stability, draft, trim, propeller immersion, and structural loading. Ballast does more than add weight. Its distribution changes how the ship sits in the water and helps compensate as cargo conditions, fuel, and other consumables change. Throughout the voyage, the crew monitors the ship's loading and stability condition. When operationally required, ballast can be adjusted according to the vessel's approved procedures, and the strange part is where that weight comes from. Ballast water is pumped straight from the ocean surrounding the ship. Sometimes the weight helping a cargo ship survive the ocean is the ocean itself. Chapter 5. The storm is part of the calculation. Stability is not just built into the ship, it is managed, minute by minute, by the officers on the bridge. When a storm appears on the weather routing display, the decisions begin. The master can alter course to avoid the worst of the system. If the worst weather cannot be avoided, course and speed become powerful tools. Changing either one changes how frequently the ship encounters the waves and how those waves act on the hull. There is no single perfect angle for every storm. The safest combination depends on the ship, its loading condition and the sea state. Speed matters. Too fast into head seas and the ship can slam violently. Reduce speed too far, however, and rudder effectiveness can begin to suffer. The officers monitor the roll period and roll angle continuously. If the vessel begins entering a dangerous rolling pattern, the bridge team may need to alter course, speed or both to change how the ship encounters the waves. The ship does not simply endure the storm, its officers manage how it meets the storm. The stability calculations made in port become live decisions made at sea, and yet, even with all of that, there is a limit. Chapter 6. When stability turns dangerous. The counterintuitive truth about ship stability is that more is not always better. A ship with extremely high metacentric height is called stiff. It returns to upright very quickly after a roll. That sounds safe, but a stiff ship snaps back so violently that the rapid motion can generate severe accelerations and enormous loads on the container lashings, dangerous to cargo and crew alike. At the opposite extreme is a tender ship with lower initial stability. Its rolls may be slower and the accelerations less violent, but the restoring margin is also smaller. Neither extreme is desirable. The goal is not maximum stability, it is the right stability. Then there are two dangerous forms of resonant rolling. In synchronous rolling, the rhythm at which the ship encounters the waves approaches its own natural rolling period. Each wave can then reinforce the motion instead of allowing it to die away. Parametric rolling works differently. As large waves travel along the length of a container ship, the underwater shape supporting the vessel repeatedly changes. A wave crest near midships can give the ship a different restoring tendency from the condition created as the crest moves toward the bow and stern. Under the wrong combination of wave period, speed, heading and loading condition, those repeated changes in stability can pump energy into the roll, and the roll angle can grow frighteningly quickly. The top of a high container stack can sweep through a wide arc with every roll, producing enormous accelerations and forces on the securing system. The crew must recognize the danger early and alter course, speed or both to move the vessel away from the dangerous condition. Water inside the ship can create another problem. In a partly filled tank or a flooded compartment, liquid can move from side to side as the vessel rolls. That moving mass shifts the effective center of gravity and reduces stability. Naval architects call it the free surface effect. Stability failures rarely come from a single cause. They emerge from combinations: heavy weather, cargo shift, water trapped on deck, a loading miscalculation, a course change delayed by minutes. The ocean does not defeat a ship with one wave. It defeats it by finding the gap between calculations. A giant ship does not stay upright because the ocean is forgiving. It stays upright because its hull, cargo, ballast and movement have all been calculated around forces most of us never see. The towering containers were never the whole story. The real answer was beneath the waterline, in the shape of the hull, the distribution of weight and ballast, the hours of stowage planning, and the decisions made on the bridge as the waves build. But keeping the ship upright solves only half the problem, because while the vessel rolls, thousands of containers still have to remain attached to the deck. Now, if you liked watching this video, like, share and subscribe to the Blue Water Arc as it explores the hidden systems, machines and operations that keeps the maritime world moving, as the ocean is far more engineered than it looks.